This is lesson 6 in the thermal physics topic and is the first lesson on ideal gases, which is the second part of the thermal physics topic. By the end of the day, you should be able to do these things, or end of the lesson, should I say. First thing we're going to look at is moles. Just read this definition of what moles are. So all a mole is it's just a measure of an amount of a substance. It tells you how many molecules you've got inside a substance. And 1 mole is defined as being 6.02 times 10 to the power of 23 atoms or molecules. Now that is a very large number. So that means if you've got 1 mole of a gas, you have got that many molecules of the gas inside your box. That is a lot of them. This number here, 6.02 times 10 to the power of 23, is called Avogadro's constant, named after a scientist called Avogadro who first stated this number. Now we have an equation, which is this: n, capital N, equals little n times Na. Now, big N, this one here, is the number of molecules. It's the number of molecules I've got that I'm looking at. N is the number of moles, and Na is Avogadro's constant, where that constant, that Na, is always the same number. It's always this. It's always 6.02 times 10 to the power of 23. And we're going to use this equation to try and calculate the number of molecules from the number of moles, and also if I know the number of molecules, how can I calculate the number of moles? As a bit of an extension, especially for chemists among you, those of you doing chemistry level, then you can start thinking about molar mass as well as a bit of an extension to this. This is a worked example of how to use that equation. So how many molecules do we have if there are 2.5 moles of a substance? Well, if I've got 2.5 moles of it, then that means my N value is 2.5, number of moles 2.5. The Avogadro constant number is always 6.02 times 10 to the power of 23. And my N, number of molecules, is what I'm looking for. Using the equation, I don't have to rearrange it, I just stick the values in, and multiplying everything out, I should come to 2 sig figs, 1.5 times 10 to the power of 24 molecules. So have a look through that. The next worked example is trying to find the number of moles if I know the number of molecules. So now I've got 4.7 times 10 to the power of 21 molecules. How many moles have I got? Same first step again. I write down the variables I know. So I know N, the number of molecules. I know Avogadro's constant. And I want to work out little n, the number of moles. The equation is this. And I'm going to rearrange it to get it in terms of little n, because that's what I want to know, the number of moles. And then sticking in my values for N and my values for Avogadro's constant, Na. Sticking in my values, I should come to 7.8 times 10 to the minus 3 moles. So you can put those into your notes as some worked examples. Can you give these questions a try now? So just pause the video here and try these. I'll show you the answers in a second. And here are the answers to the first 3. And for the challenge questions, these are questions that you should have a go if you read through that extension bit at the beginning, especially if you're A-level chemistry, you can give these a go. Should have got 9.4 times 10 to the power of 24 and 3.9 times 10 to the power of minus 22 grams. So looking on now more to thinking about pressure in an ideal gas, I want you to have a think about what would happen if this astronaut just decided to suddenly open up their visor. What would happen? Well, if their lungs were full of gas, if they're taking a breath in and they open the visor out, the gas would rush out because there'd be a pressure imbalance between the pressure of gas in their lungs and the pressure of the vacuum outside. So the gas would just come up through their lungs and smash through their teeth if they had their mouth closed. So that would be a pretty unfortunate position to find yourself in. But why would that happen? So let's have a think now about ideal gases and pressures and what causes pressure. Before we get to pressure, we're going to make some assumptions. So to understand how gases exert a pressure, we're going to make some assumptions so that our model is easier to understand. This is 5 really important points that you must have in your notes. So please make sure that you've all got them in your notes. There are 5 assumptions for an ideal gas, and a common exam question is to list them. Number 1, read it through. So we assume we have loads of atoms or molecules, very large numbers, sort of on the order of numbers of moles, so sort of times 10 to 23 number. And they're moving in random directions with random speeds. Number 2, read it through. So the particles basically are really, really small compared to the total volume of the gas. So if you were to add up the volume of all of the particles, that would be negligible compared to the volume the gas takes up, which basically means that if you've got gas in a box, most of the space is empty space, the space between the particles. Read through number 3. So this means that whenever particles collide with each other, or whenever the particles hit into the wall, the collisions are perfectly elastic. Can you remember what an elastic collision means? It means that kinetic energy is conserved. So it means that whenever there's a collision between particles and particles, or particles and walls, kinetic energy is conserved. Read through point number 4. What this means is that the time that particles spend colliding is much less than the time they spend between collisions. So most of the time particles are flying around, not hitting into anything, and every now and then they will hit with something, but that time is much less than the time they spend just flying around, not being hit into things. And read through the 5th assumption and the final assumption. So it means that when particles are flying around, the forces between them are negligible. There's basically no electrostatic attraction between the particles when they're not colliding with each other. So we're going to have a think now, what do these assumptions make our gas look like? And I'm going to go to this simulation, and I'll leave a link as well so that you can try it at home. So taking all of those assumptions into account, we would come up with a model that looks a bit like this, where you've got particles flying around, and if you look at the particles, you can see that particles are all moving at different speeds, and all the particles are moving in different directions. You can see that the particles, although not perfect on this simulation, are much smaller than the total volume of the gas. And what is quite nice in this model is that it allows us to link the temperature of the gas, the volume of the gas, which I can change if I wanted to, and the pressure of the gas. So I can increase the volume, see how that affects things. I can heat up my gas with some fire. I can cool down my gas with some ice. And it allows us to see how these other variables change, which will be really important in the next lesson when we look at the ideal gas laws. So how can we prove that all of this causes pressure? Well, pressure is a force on the wall. So what we've got is before an atom hits the wall, your atom is moving along in this direction with this momentum, mass times velocity, mu. So it's got a momentum in this direction before it hits the wall. Our particle then hits the wall and bounces back in the opposite direction. And its momentum before was to the right, its momentum now is to the left. So its momentum has changed, it's changed direction. We could calculate the change in momentum, and it would be the final momentum minus the initial. So the change in momentum would be minus mu, minus the initial, mu, and it would give us minus 2mu. And there's change in momentum means there must have been a force. That's Newton's second law. Wherever you've got a change in momentum, must be a force. So the force on the particle is pushing it to the left to give it that negative change in momentum. And then using Newton's third law, can you remember what that is? It's when you've got equal and opposite forces on opposite bodies in opposite directions. So where my wall is pushing my particle to the left, my particle in that collision must have been pushing the wall to the right. So this pressure force comes from the particles bouncing off of the wall. And when you add up all of the collisions with every single particle hitting the wall, it turns out that there's quite a lot of force, and that is what gives you your pressure. Pressure is force over area. How can you increase the pressure by changing the volume? How does changing the volume increase the pressure? Well, imagine these are my 5 particles, and at first they're in a pretty big box with a large volume. If I decrease the volume, the particles, they're not necessarily going to be moving any faster. I'm going to be keeping it at the same temperature, so they're not moving any faster. But because there's less distance between the walls now, they're going to be colliding with the walls more often. And if you've got more collisions, which are happening more and more frequently, then the pressure is going to go up. So decreasing the volume increases pressure because particles collide more often with the wall. So inversely proportional relationship between volume and pressure. We'll look at that in the next lesson a bit more. How can pressure be increased by changing temperature? Well, if I have a cool gas, the atoms aren't moving very quickly. So there will be very few collisions with the wall, and the collisions won't be very energetic. There's not going to be a lot of force in each collision. But if I have a hot gas, the particles move around faster, which is being shown with these longer arrows. So there's going to be more collisions. If they're moving around faster, they're going to be hitting into the walls more often. And each collision will be more energetic. So because you've got more force in each collision and more collisions, there will be more pressure in total. So you can summarize it with these 2 bullet points. Faster particles means a greater force, therefore more pressure. And faster particles means more collisions, and therefore more pressure. Once you've finished this, make sure you do the quiz on the kinetic theory of ideal gases.